Anna Bergstrom was 24 years old when she started digging a hole in the Dakota Territory prairie that would become the most ridiculed and eventually most admired dwelling in the entire settlement of New Uppsala. It was May 1867, and Anna, a widow for 8 months after her husband Eric died in a logging accident, had just filed her homestead claim on 160 acres of grassland that everyone else considered worthless because it had no timber and minimal water. Eric's death had left Anna with $40, a wagon, 2 horses, and the choice between returning to her family in Minnesota as a dependent or proving she could survive independently on the frontier. She chose independence and filed her claim under the Homestead Act, becoming one of the few single women attempting to prove up land in Dakota Territory. The conventional wisdom in New Uppsala was clear. Proper housing meant sod houses built above ground with walls stacked from prairie sod bricks, or if you had money, frame houses built from expensive imported lumber. What Anna proposed was neither. She planned to build a pit house, a semi-subterranean dwelling dug partially into the earth with walls rising only 3 feet above ground level. The design was inspired by what she'd observed about native Mandan earth lodges during her travels west, combined with her understanding of how root cellars stayed cool in summer and warm in winter. If underground spaces naturally moderated temperature, why not build an entire house partially underground rather than fully above ground, where it would be exposed to harsh Dakota weather? Her plan was technically sophisticated, despite appearing primitive. She'd excavate a rectangular pit approximately 18 feet by 24 feet, going down 4 feet below ground level. The floor would be at -4 feet. The walls would rise from that excavated floor to approximately 3 feet above original ground level, creating total wall height of 7 feet, adequate for standing and living. But 3/4 of that wall height would be below ground, insulated by earth. The above-ground portion would be built from prairie sod bricks, the classic building material of treeless plains. But the below-ground walls would be lined with stacked stone where possible to prevent earth collapse and provide drainage. The roof would be supported by a center pole with radiating rafters covered with layers of grass, sod, and earth, creating a living roof that would blend with the prairie. Most critically, she'd incorporate a thermal chimney system, a vertical shaft rising from the lowest point of the floor through the roof peak. This shaft would create natural convection, warm air rising and drawing cooler air down, creating constant, gentle circulation without mechanical systems. She'd read about similar principles in mine ventilation and realized the same physics could provide fresh air circulation in an earth-sheltered dwelling. She began excavation in mid-May with tools purchased with half her remaining money: a good spade, a pick, a wheelbarrow. The excavation for an 18 by 24-foot pit going 4 feet deep required removing approximately 432 cubic yards of prairie soil. At perhaps 2 cubic yards per day working alone, that was 216 days of excavation, 7 months of sustained digging. The physical reality was crushing. Dakota Territory prairie soil was heavy clay loam, with dense grass root systems extending 3 feet deep. Each cubic foot weighed perhaps 100 pounds. She'd dig, breaking through the root mat, filling her wheelbarrow, pushing it up a ramp out of the growing pit, dumping it on what would become her roof later, returning for another load. The work destroyed her hands within days. Blisters formed and broke and bled. Calluses built up over weeks. Her back was in constant pain from the bending and lifting. Her shoulders burned. She lost weight despite eating her full rations because the caloric expenditure exceeded intake. But she worked systematically through May, June, July, August. 4 months of sustained excavation. The community reaction was immediate mockery. By June, when the pit was clearly visible and Anna's intentions were obvious, the women of New Uppsala organized an intervention. Margareta Johansson, the settlement's unofficial social leader, visited Anna's claim in late June with 5 other women. Found Anna waist-deep in her excavation, covered in dirt, looking like something between a farmer and a grave digger. "Anna, dear, this has gone far enough. You're digging a hole in the ground. This isn't housing, this is insanity. You're planning to live underground like a prairie dog or a savage. It's undignified, it's dangerous. Please accept the Lindstrom family's offer. They need household help. Room and board plus $3 monthly. That's proper work with proper housing." Anna, standing in her 4-foot-deep pit, looked up at the 6 women arrayed at ground level above her. Understood how the visual reinforced their point. She was literally below them, in a hole, covered in dirt, appearing desperate and foolish. This pit house will provide better insulation than any above-ground sod house. The earth surrounding the walls moderates temperature. The sunken design protects from wind. The thermal chimney provides ventilation. This is engineering, not savagery. It's a hole. You'll be living underground. Water will seep in. The walls will collapse. You'll freeze in winter or drown in spring. This is suicide built from stubbornness. Please stop before you kill yourself." Anna thanked them for their concern and continued digging after they left, certain they'd be proven wrong when winter came and her pit house outperformed their conventional housing. By late August, the excavation was complete. The pit was 18 by 24 feet, 4 feet deep, with sloped ramps at the entrance for access. The work had consumed her physically and mentally. She'd lost 15 pounds, aged visibly, developed permanent changes in her hands and posture. But the hole was dug. The floor preparation was critical and required understanding drainage principles most builders ignored. She'd added 6 inches of gravel she'd hauled from a creek 3 miles away, 30 wagon loads over 2 weeks, perhaps 15 tons of gravel total. The gravel layer served multiple purposes, provided drainage, preventing standing water, created capillary break, preventing moisture wicking up from earth below, provided stable base for living. Over the gravel, she'd laid a thin layer of clay she'd puddled and tamped, creating moisture barrier. Over that, another inch of sand for final floor surface. The result was a floor that would drain, wouldn't wick moisture, and provided solid walking surface. The engineering was sophisticated, despite using only earth materials. Now came the wall construction, which would determine whether the structure succeeded or failed catastrophically. The below-ground portions were most critical. These walls had to resist earth pressure from outside while preventing moisture infiltration. She gathered fieldstone wherever she could find it, backbreaking work, hauling 100-pound boulders in her wagon. Where stone was available, she'd line the below-ground walls with dry stacked stone facing. The stone served multiple purposes. Prevented earth from crumbling into living space, allowed drainage water to flow down rather than through the wall, provided some thermal mass, created durable surface that wouldn't erode. Where stone wasn't available, and she couldn't gather enough for all walls, she carefully shaped and packed the earthen walls, cut them at slight inward angle for stability, smoothed the surface to prevent erosion. The technique was similar to what she'd observed in native earth lodge construction, but adapted for her specific conditions. The above-ground portions were built from prairie sod bricks, and here Anna implemented her most significant innovation, double-wall construction with insulating air gap. Prairie sod cutting was brutal labor requiring specific technique. She'd select areas where grass root mat was thickest, usually virgin prairie that had never been plowed. Using a special plow blade she'd borrowed, she'd cut strips of sod 3 feet long, 1 foot wide, 6 inches deep. Each strip weighed approximately 50 pounds, solid mass of interwoven grass roots, soil, and organic matter. She'd cut, then carefully lift each brick to avoid breaking it. Load onto her wagon, perhaps 20 bricks per load, 1,000 pounds total. Haul to the building site. Stack carefully with proper overlapping technique, so joints didn't align vertically, creating weakness. The double wall innovation required meticulous execution. She'd build inner wall first, laying sod bricks in running bond pattern, each course offset from the one below. Build this inner wall to full height, then leave a 6-inch gap. Build the outer wall parallel to the inner wall, again in running bond pattern. The 6-inch air gap between walls was her critical thermal innovation. Still air is excellent insulator. That's why down jackets and double-pane windows work. The air trapped between her double sod walls couldn't circulate, couldn't transfer heat by convection. It provided perhaps R3 to R4 additional insulation beyond what sod walls already offered. Building double walls required twice the sod bricks, approximately 800 bricks instead of 400 for single wall construction. She cut, hauled and laid every single brick herself over 6 weeks of sustained labor. The physical cost was immense, but the thermal performance would be transformative. For the roof, she'd set a center pole, a cottonwood trunk she'd hauled 20 miles from the nearest river. The pole was 10 inches in diameter, rising from floor level, -4 feet from grade, to 8 feet above original grade, total height 12 feet. From this center pole, she'd run rafters radiating outward to the perimeter walls. Over the rafters, she laid prairie grass in thick layers, then sod bricks, then more earth. The finished roof was nearly 2 feet thick, massive insulation that would moderate temperature swings dramatically. The thermal chimney was her most sophisticated element. At the lowest point of the floor, she'd positioned a vertical shaft made from stacked sod blocks, forming a 12-inch square column rising from floor level through the roof peak. This created a vertical path for air movement. Warm air, being less dense, would naturally rise through this shaft. As warm air exited the top, cooler air would be drawn in through the entrance, creating gentle, natural ventilation. She tested the chimney effect before completing the roof by lighting a small fire inside. Watched smoke naturally drawn up and out through the chimney shaft. No forced draft, just natural convection. The system worked exactly as physics predicted. By late September, the structure was complete. From above ground, it appeared as a grass-covered mound barely 3 feet high, with a doorway entrance descending into earth. Inside was a 7-foot-high space, 18 by 24 feet of usable floor area, 432 square feet total. The walls were earth and sod. The floor was gravel over earth. The ceiling was layers of grass and sod, supported by cottonwood rafters radiating from the center pole. The interior was dark. She'd included 2 small windows, expensive glass she'd bought in a moment of extravagance, but they provided minimal light. The space smelled of earth and grass. The walls were cool to touch. The floor was solid, but clearly underground. Everything about it screamed primitive to people accustomed to conventional housing. She moved in October 1st. Brought her minimal possessions, a rope bed frame, a small stove, vented through a separate flue, not the ventilation chimney, a table, 2 chairs, her trunk of clothing and keepsakes from Eric. Made the pit house her home. The ridicule intensified. Anna Bergström was living in a hole in the ground, like an animal in a burrow, like a savage in an earth lodge. She'd spent 4 months digging and building what amounted to a grave she inhabited. The woman was clearly unwell. Grief over Eric's death had driven her to this undignified situation. Through October and November, Anna discovered the pit house performed exactly as she'd predicted, and better in some ways she hadn't anticipated. The learning process was daily education in practical thermodynamics. The temperature stability was the most dramatic advantage. Outside, Dakota autumn weather was violently unstable. 70-degree warm afternoons could drop to 25-degree cold nights within 12 hours. The temperature swings were extreme and unpredictable. Inside the pit house, temperature varied between 52 and 58 degrees, with absolutely no heating. She documented this carefully, taking thermometer readings morning and evening, fascinated by the stability. While outside temperature swung 45 degrees daily, inside varied only 6 degrees. The Earth insulation was working exactly as physics predicted. The massive thermal mass resisted rapid temperature changes. The sunken design provided wind protection she hadn't fully appreciated during planning. Dakota wind was relentless. Sustained 20 to 30 miles per hour was normal, 40 to 50 common during storms. That wind would assault above-ground buildings continuously, finding every gap, creating pressure that forced cold air through walls. Her pit house, with 3/4 of its wall height below grade, was protected by the earth itself. Wind flowed over the low-profile structure, only 3 feet of wall projected above ground. There was nothing for wind to push against. The mound shape was aerodynamic. Inside, she couldn't hear wind the way above-ground dwellers did. It was muffled, distant, non-threatening. The thermal chimney created ventilation patterns she could actually observe. She'd light incense sticks and watch smoke behavior. Could see smoke naturally drawn toward the floor-level chimney opening, rising through the shaft, exiting at roof peak. Meanwhile, fresh air flowed in through the doorway at floor level, warming as it crossed the interior. The system was completely passive. No fans, no pumps, no mechanical systems. Just natural convection driven by temperature differences, warm air being less dense than cold air, rising naturally, creating pressure difference that drew fresh air in. The continuous, gentle circulation prevented stuffiness and controlled humidity without energy input. The acoustic environment was unexpectedly pleasant. Earth-sheltered spaces have unique sound characteristics. External noise was heavily dampened. The 4 feet of earth surrounding below-grade portions absorbed sound remarkably well. Inside sounds didn't echo harshly like in timber structures. The sod walls and ceiling absorbed sound, creating quiet, intimate acoustic environment. She'd lie in her rope bed at night, listening to subtle sounds. Earth settling slightly as temperature changed, grass roots in the roof continuing to grow and adjust, moisture moving through drainage systems. The house was alive in subtle ways conventional construction wasn't. Her fuel consumption was dramatically lower than neighbors. With small morning and evening fires, perhaps 5 pieces of wood daily, she maintained comfortable 60 to 65 degrees. Her neighbors in above-ground sod houses burned 20 to 30 pieces daily, maintaining similar comfort. The mathematics were clear. She was using 1/4 the fuel for equivalent heating. The cost savings were significant. Firewood in Dakota Territory was expensive, had to be hauled from distant river valleys. Buffalo chips were alternative but also required gathering labor. Reducing fuel consumption by 75% meant Anna could survive on minimal cash income while her neighbors struggled with heating costs. December brought cold that tested everything. Outside temperature dropped to 0 degrees and stayed there for days. Anna's pit house, with its earth insulation and sunken design, maintained baseline 50 degrees with no heating. A small morning and evening fire raised it to 65 degrees, comfortable enough for living. Her neighbors were struggling. The above-ground sod houses, despite thick walls, were losing heat rapidly. Cold air infiltrated through gaps. The thin roofs provided inadequate insulation. They burned fuel at unsustainable rates, maintaining barely adequate temperature. Then December 23rd brought the blizzard that proved everything and transformed how New Uppsala understood the relationship between housing design and survival. The warning signs began December 22nd evening. Temperature dropped from 15 degrees at noon to 0 by 6 p.m. to -10 by midnight. The drop was too rapid, too sustained. Veteran Dakota settlers recognized the pattern. Arctic air mass moving in fast, bringing sustained, dangerous cold. The storm hit dawn December 23rd, Christmas Eve, with catastrophic intensity that even experienced frontier settlers recognized as potentially deadly. Temperature -15 degrees by 6 a.m., -20 by 9 a.m., -25 by noon and staying there. Wind building steadily, 30 miles per hour at dawn, 50 by mid-morning, sustained 70 with gusts to 90 by afternoon. Snow began falling around 7 a.m. Not gentle holiday flakes, but dense heavy snow, falling at 4 to 5 inches per hour, driven horizontally by screaming wind. By 9 a.m., visibility was absolute zero. You couldn't see your hand at arm's length, couldn't distinguish sky from ground. The world became white chaos and noise that sounded like continuous roar. Anna was in her pit house when the storm arrived, having completed morning chores and descended to her underground shelter before conditions deteriorated fully. She'd pulled the heavy insulated door shut, a door she'd built specifically for this structure, heavy timber with buffalo hide covering for additional insulation. Inside, she could hear the storm, but it sounded distant, muffled. The wind roared somewhere above and outside. She could hear it through the earth covering, but it didn't penetrate to her living space. Could feel very subtle pressure changes as the massive storm system moved overhead. But the storm was happening in a different world from her earth-sheltered space. She took thermometer readings documenting performance. At 9 a.m., when the storm was building, interior temperature was 54 degrees with no fire burning. She lit a small fire in her stove, perhaps 3 pieces of wood. By 10 a.m., interior was 60 degrees. She let the fire die to coals. Through the day, as -25 temperature and 70-mile-per-hour wind raged outside, the pit house temperature dropped very slowly. By 6 p.m., 57 degrees, only 3-degree drop despite 12 hours of extreme conditions. The earth insulation was working magnificently. The thermal mass of soil surrounding the structure was protecting her from temperature extremes happening mere feet away. Above ground, conventional sod houses were experiencing catastrophic failure that would kill people before the storm ended. The Johansson house was typical above-ground construction, good quality by Dakota standards. Thick sod walls maybe 3 feet wide, sod roof about 18 inches thick, proper construction by experienced builders. But it was above ground, fully exposed to the storm. By 9 a.m., when the storm intensified, their house was losing heat rapidly. The 70-mile-per-hour wind created pressure that found every microscopic gap in construction. Cold air was being forced through the walls despite thickness. Heat was escaping through the roof. The interior temperature was dropping despite the stove burning continuously. Margareta Johansson fed the stove constantly. Precious wood and buffalo chips consumed at rates she knew were unsustainable. By noon, with the stove roaring hot enough to glow red in places, the house interior was 48 degrees. Outside was -25. They were losing the battle. By evening, December 23rd, 38 degrees inside, despite burning furniture when fuel ran out. The family, Margareta, her husband Olaf, their 3 children, ages 8, 5, and 3, were wearing every piece of clothing they owned layered together, huddled together for body heat, burning chair legs and table planks, watching helplessly as the temperature continued dropping. By morning Christmas Eve, December 24th, the situation was desperate and deadly. The house interior was 35 degrees. Little Ingrid, the 3-year-old, was showing severe hypothermia symptoms. Lethargy, confusion, dangerous respiratory depression, skin grayish-blue, pulse weak and slow. The child was dying indoors despite being in what everyone considered proper housing. Margareta made desperate decision. Remembered Anna's pit house was maybe 300 yards away. Didn't believe it could be warmer than proper housing, but had no other options. Decided to risk the journey. They dressed in every layer they owned, tied themselves together with rope to avoid separation, left their failing house and entered the blizzard. The journey was nightmare, 300 yards through -25 cold and 70-mile-per-hour wind with zero visibility. Took 30 minutes of sustained terror. Arrived at Anna's location barely conscious. Found the pit house entrance, a doorway descending into earth, partially drifted with snow. descended the ramp, pounded on the door. Anna opened it. Warm air rolled out, not blazing hot, just noticeably warm compared to killing cold outside. 60-degree air meeting -25 created visible vapor. 5 frost-covered people stumbled into Anna's pit house, collapsed on the floor. Anna got them lying near her small stove, wrapped them in her blankets, watched color slowly return to Ingrid's grayish skin as the stable 60-degree temperature prevented further heat loss. Margarita, recovering enough to speak, looked around the pit house she'd called a hole and an embarrassment. The earthen walls, the grass-covered ceiling, the space that was indeed mostly underground, but it was 60 degrees. Her proper house had been 35 degrees and failing. This pit house was saving her family's lives. "How?" she asked simply. "How is this warm? My house with proper walls can't stay above freezing. Your hole in the ground is comfortable." "How?" Anna explained patiently. The earth surrounding the living space provided massive insulation, 4 feet of soil on all below-ground sides, 2 feet of sod roof above. That thermal mass prevented rapid temperature changes. The sunken design meant wind couldn't directly attack the walls. The earth itself protected the structure. The thermal chimney provided ventilation without creating cold drafts. Your above-ground house has thin roof and walls exposed to direct wind. The wind at 70 miles per hour creates pressure that forces cold air through every gap. Heat escapes through the roof. My pit house is protected by earth. The storm is happening above me. But down here at -4 feet from grade, the earth itself is my insulation and protection. 7 people sheltered in Anna's 432-square-foot pit house for 3 days while the blizzard raged. Tight but manageable, the space maintained 60 degrees with her small fire. Everyone survived comfortably, while conventional houses throughout New Uppsala struggled or failed. When the storm ended December 26th, they emerged to find New Uppsala devastated. Multiple conventional houses had interior temperatures below freezing. 3 families had lost members to hypothermia, livestock frozen. The community traumatized by the worst blizzard anyone had experienced. But Anna's pit house had functioned perfectly. The earth-sheltered design everyone mocked had proven superior to conventional construction. The transformation in community perception was immediate and complete. The pit house wasn't crazy. It was brilliant practical engineering using available materials and physics to create superior shelter. Within days, 5 families asked Anna to advise on building their own pit houses. She helped design and supervise construction of 4 earth-sheltered dwellings before spring. Explain the principles. Excavation depth matters, drainage is critical, thermal mass works, wind protection through earth covering is superior to fighting wind with thin walls. Anna lived in her pit house for 8 years, eventually marrying a surveyor who respected her engineering knowledge. They built a larger conventional house, but kept the pit house as storm shelter and demonstration of earth-sheltered design principles. She died in 1912 at age 69. Her obituary mentioned her as the widow who built the famous pit house of New Uppsala. The structure itself survived until 1935, when it was finally filled in, though the entrance ramp depression is still visible on the prairie. Modern thermal analysis of her design confirms the efficiency. 4 feet of earth provides approximately R8 to R10 insulation value. The massive thermal mass dampens temperature swings. The sunken design eliminates wind pressure on walls. During the blizzard, while surface temperature was -25, the temperature at -4 feet depth was approximately 40 to 45 degrees. Anna's pit house had to heat from 45 to 60 degrees. Conventional houses had to heat from near -25 to 60 degrees, requiring vastly more fuel. The story is about a widow who understood that proper housing isn't defined by convention, but by performance, who proved that building partially underground isn't primitive. It's intelligent use of Earth's natural insulation, and whose ridiculed pit house saved lives when expensive conventional housing failed. Because sometimes the person living in a hole knows more about shelter than people living in houses. The earth covering everyone called undignified was actually superior insulation. And natural physics matters more than social conventions when winter tests everything.